Okay, so let's assume that the Dallas Cowboys actually get to play this fall amidst the coronavirus. And so they are playing football and they've got the roof open to the stadium. Okay. So you've got the Jumbotron up here. And the Jumbotron is roughly 21.9 meters. And let's say that it is a distance of 89.1 meters above the playing field down here. And then somewhere up above here, there's a pigeon sitting up here. And the pigeon, well, does what pigeons do. Okay, and so now a piece of pigeon dropping starts falling down here. Now we're going to ignore air resistance. Okay, and so you're watching this and you see the pigeon droppings cross the scoreboard in 1.15 seconds. Okay, to cross the scoreboard. So what I want to know is, ignoring air resistance, how fast is the pigeon droppings move? How fast is this moving when it hits the playing field down below? Okay, all right. So we look at this problem and we say, well, gosh, how do we solve this problem? Okay, and we look at it and we realize that there are three parts to the problem. Part A, Part B, Part C. So Part A is above the scoreboard, Part B is crossing the scoreboard, Part C is below the scoreboard. Now we only have two equations. X equals x naught plus v naught t plus 1/2 a t squared. And then v equals v naught plus a t. Okay, so let's say I have two questions for you. I want to know how high was this pigeon above the scoreboard, and then two, how fast was this moving down here at the bottom? Okay, so I have two questions. How high above the scoreboard was the pigeon? Okay, so above the scoreboard, the only thing we know here is the acceleration due to gravity is the same on all parts of this problem. Okay, so what do we do? Well, we look at it and say above the scoreboard, we don't know a whole lot. We know it starts from rest, so V naught is going to be 0 up here, okay, and then X naught is 0, but we don't know the time and we don't know the distance, so we can't really solve that, okay. For below the scoreboard, we don't know the time, okay, so we can't really, and then we don't know how fast it's moving, so initially, because it's already moving by the time it gets there, so that's going to be tough. Okay, so, but across the scoreboard, we know the time, we know the acceleration, we know the distance. In fact, the only thing we don't know is the initial velocity being the velocity at the top of the scoreboard. So that means we ought to be able to solve that to find the velocity at the top of the scoreboard. If we know the velocity at the top of the scoreboard, we can find out how long it took to get to that velocity, which means we could then figure out how far it fell. And then once we know that, this distance, and this distance, we know the total distance, so we can find the total problem. So crossing the scoreboard. This is part B of the problem. Okay. So 1.15 seconds, we know that the distance was 21.9 meters. So x equals x naught plus v naught t plus 1/2 gt squared. I'm going to say that down is positive. We know the acceleration is down. Okay. So I'm going to say that x naught is 0. So we do some algebra here. And we find that V naught equals x over t minus 1/2 gt. Okay, so that'll be, well, we know all these terms. We know 21.9 meters divided by 1.15 seconds. minus 1/2 9.81 meter per second squared times 1.15 seconds. So V naught is going to be equal to 13.4 meters per second. So that's how fast it's moving right there at the top of the scoreboard. Now, for part A of the problem, so we have the pigeon and the droppings fall to the top of the scoreboard. So we know the velocity at the top of the scoreboard is 13.4 meters per second. So we can then look at that and say, wait, now we know the velocity at the top of the scoreboard. Okay, if we know the velocity at the top of the scoreboard, then we know that V is V naught plus GT. So we're assuming the V naught is 0, the pigeon's not moving, just sitting there. And so that means we know T. T is going to be V over G. So 13.4 meters per second divided by 9.81 meter per second squared. And so that's going to be 1.37 seconds. Okay, so the distance x, okay, x naught plus v naught t plus 1/2 gt squared. All that's 0, so x is just 1/2 gt squared. Okay, so x is going to be 1/2 9.81 meter per second squared times 1.37 seconds squared. So x is going to be a distance of 9.15 meters. Now we have the entire problem. We have found that this was 9.15 meters. We were given that the distance across the scoreboard was 21.9 meters. We were also given that this was 89.1 meters. So the total distance, you just add up all those, that's 120.2 meters. So we know that so now we know the total distance. Okay, knowing the total distance means we have more than one way of solving the problem. So we know that x equals 1/2 gt squared. Okay, so I could solve for t. Okay, and we know that v is going to be equal to g times t. Now, I could solve for t and get a number and plug in the other equation, or t equals square root 2x over g. Well, if v is going to be gt, that's going to be g times the square root 2x over g. So that's the square root of 2xg. Okay, so I don't have to do the in-between step of calculating this and then plugging it in. I could actually substitute and then do this all in one step. So that this is going to be v equals square root of 2 times 120.2 meters times 9.81 meter per second squared. Okay, and that comes out to be 48.6 meters per second. Okay, so now the question is, which is preferable? Actually doing the calculations here and plugging in the number, or substituting algebraically and doing it? Well, different people have different strategies. One person says one way's better, one person says another way's better. If you're actually doing this computationally, writing a computer program to do it, there's fewer rounding errors if you put it into this form right here. If you do it the other way and then carry decimals out and so forth, that should work also. Doesn't really matter. You should get the same result in the end. And so which way is better doesn't really matter. I like sometimes doing it algebraically and then putting numbers in at the end, because I find that I am more likely to make a mistake pressing buttons in the calculator, and the fewer buttons I push, the fewer mistakes I make. Other people may find that they are more likely to make an algebraic mistake, and so it's easier on them to use the calculator. It matters not to me. Do whichever works best for you. But here's another. This is another example. This is a little more complex example because we have three parts to the problem, and we'll point out there's a very similar problem I gave on a test one. So I did a problem very much like this, and on the test, I said that we had a car and starts off from rest and reaches a bridge, and I gave them the distance across the bridge, that distance, and I told them how long it took to cross the bridge, okay, and then I gave them how fast it was moving at the end down here, and I asked them to give me that initial distance right there. Okay, now a lot of students looked at that and they panicked and they did not recognize the problem. But basically, this is essentially the same problem turned sideways. So this is pretty much the same problem that was turned sideways. And so all you have to do is same thing. You solve here for the initial velocity, find the acceleration, and so forth. And so I think in this case, I gave the velocity at the end, and so you had to solve for the acceleration instead of me giving you the acceleration. But it is all basically the same problem. What you'll notice is that there's only so many different kinds of questions you can ask. That's why you do so many homework problems. The more homework problems you do, the more practice you have solving problems. And so on a test, when I ask a problem, you will go, oh, wait, I remember doing something kind of like that. Or else you'll start it and then realize, hey, this is similar to what I've done before. And then it makes the problem a whole lot easier.